Hi everyone, my name is Shuang Yang and my ZID is 5576850. This is my student ID card. So first, I will briefly explain the Kepler's law because they are the main ideas behind this experiment. Kepler's first law says that the planets move around the Sun in elliptical orbits, with the Sun at one focus. And Kepler's third law says that the planets sweep out equal areas in equal times. This means the planet moves faster when it is closer to the Sun, and slower when it is farther away. Kepler's third law says that planets farther from the Sun take longer to complete one orbit. For question 9, I changed the simulation from the Sun-planet to the planet-moon system. What I noticed was that the planet did move slightly as the moon orbited. I had first expected the moon to just move around the planet, but after watching more carefully, I could see that the planet was not completely fixed. This helped me understand the century of mass better. In the Sun-planet system, it stays very close to the Sun, but in planet-moon system, the planet's movement is easier to see because the mass difference is smaller. For question 11, I used the measuring tape to check the distance from the Sun to the Earth. It's close to 1 AU, and I could see that the distance covered about 2 grid space. So 1 grid space represented about 0.5 AU. This step was actually very important. If I got the grid spacing wrong, then all of the orbital distance I recorded afterwards would also be wrong. For question 12 to 14, I test 4 different orbital distance and adjust the velocity each time until the orbit was as close to circular as I could. At 0.5 AU, the orbital period was 97 Earth days. At 1 is 366. At 1.5 is 573. And at 2 AU, the orbital period was 988 Earth days. I think 1 AU result is especially useful because it came out at 366, which is very close to Earth's normal orbital period. And also, while doing these trials, I noticed that the changing the orbital distance alone was not enough. I had to keep adjusting the green velocity arrow to get something close to a circle orbit. If the velocity was too low, the orbit would fall inward and become much more curved. And the velocity was too high, the orbit would stretch out too much. In my view, this result still follows Kepler's law. The overall pattern is that the distance from the Sun increased, the orbital period also increased. The closest orbit at 0.5 AU only took 97 days, while the farthest one took 988 days. For question 15, the planet in our solar system with the farthest orbital velocity would be Mercury, and the slowest would be Neptune. The reason is connected to the gravity. Planets that are closer to the Sun experience a stronger gravitational pull, so they need to move faster to stay in orbit. Overall, this experiment helped me understand orbital motion much better than just reading about it. Before doing it, Kepler's laws were mostly just definitions to memorize. After doing the simulation, I understood them more as relationships that I could actually observe. For example, I could see the orbit shape changes when velocity changes, which connects to why some orbits are more elliptical. I could also see that the planets move faster when they are closer to the Sun, which links to Kepler's second law. Most importantly, the data I recorded show that the planets farther away take longer to complete one orbit, which directly supports Kepler's third law. So I think the biggest thing I learned from the experiment is that the gravity, speed, and distance are all work together. You cannot really understand orbit motion by looking at only one of them. So doing the experiment made me much clearer than the theory itself. Thank you. This is the reference list.